Spatial representations of rigid bodies. We will start by looking at exponential coordinates. First, we will see the derivative of a rotational matrix. We know that for all rotational matrices, this holds true. If we take the derivative of this term and this term, we get this expression. Then we can apply the chain rule to the first element, and then the derivative of the second element is equal to 0, and we will get this expression. Now we can reorder these elements. We can pass one term to the other side of the equality, and it will pass with a negative sign, so it will have this form. We can still reorder this and express it as a transpose of this element. And we can realize that this is actually a skew-symmetric matrix. And we will call this a skew-symmetric matrix W hat. So W hat will be, by definition, this term. Later we will see that this is equivalent to the angular velocity. The derivative of a rotational matrix can be obtained by solving this equation. So we solve for r dot here, and we get this expression. And this is also called the fundamental equation of rotational motion. It says that the derivative of the rotational matrix is the angular velocity in matrix form times the rotational matrix. The solution when the initial rotation is equal to the identity is this. The way to obtain this is similar to the way that we solve a differential equation. So you can recall that if you have a differential equation that takes this form, the solution is this one. And here it is exactly the same. And you can see that here there's an exponential. And that's why these are called exponential coordinates. As I said before, this omega hat represents the angular velocity. Now this omega hat is a skew-symmetric matrix. Consider a vector omega, which will be the angular velocity. The skew-symmetric matrix associated with this vector is this one, and by definition it's this matrix. The properties of a skew-symmetric matrix are the following. The first one is of course a skew-symmetry, which says that the negative of the transpose is equal to the same matrix. And the second property is the cross product. It says that the cross product between omega, this omega vector, and a vector p is equal to the matrix form, this matrix, times this p. So this is a matrix multiplication, but this is a cross product. The advantage of using the matrix multiplication is that we can use all the elements of linear algebra here. Let's see an example. It says that a rotational matrix represents a rotation of theta about axis x. We want to find the angular velocity associated with this rotation. We know that the angular velocity is represented by the skew-symmetric matrix. We have this matrix here, and this represents the rotation of theta about axis x, and we know this from the previous class. So we have this expression, which is the angular velocity in matrix form, and we have this matrix R, which is a rotation about x but transposed, and then we get the derivative of this matrix R. Now for the derivative we apply the chain rule, so we take first the derivative with respect to theta and then theta dot. That's why you see here at theta dot in every term. And if we operate this is equal to this term. Now if we convert this from this omega hat to just omega, we will get at the end that the angular velocity is this one, which makes of course sense because we are just rotating about x. So you see that this really makes sense. We are rotating about x and the angular velocity only has an x component. Matrix exponential. The matrix exponential is this expression, which is equivalent to the rotational matrix. There exist several ways to solve this. The way that we're going to see here is using the Taylor expansion. This is the Taylor expansion of the exponential. Now here you see that there are terms that have powers 2, 3, 4, 5, etc. So we have some properties. For example, a hat squared is equal to this expression, and this is equal to this expression. You can show this by expanding all the terms. So you expand the terms here, you expand the terms here, you expand the terms here, and you will see that both hold true. Using these two elements, you can show that this all holds true. Now we're going to replace these properties here. If we replace those properties here, we will get something like this. Now, here you see that this resembles the cosine and the sine, the expansions of the sine and cosine. But there's a problem, that here we need all 3, 3, 3, 5, 5, 5, but I have 3, 3, 2, and I have 5, 5, 4. So I need one more term of omega here and omega here. So if I add one term here, I have to divide this by one term. Also here, I have 4, 4, I need 4. I have 6, 6, I need 6. So I need omega squared here. And so I will divide also this by omega squared. That's why you have here divided by omega and divided by omega squared. And this is the expansion of the sine, and this is the expansion of the cosine. Actually, this is 1 minus the cosine. So at the end, you get this expansion of the Taylor series as a function of sines and cosines. The advantage of this over this pure Taylor expansion is that the first one is infinite. It's an infinite series. This one is not an infinite series, so it's more convenient for computing it. The generic interpretation of this matrix is that this generic exponential matrix represents a rotation with an angular vector velocity for a time t. So this is a rotation about an axis given by the angular velocity for a time t. If we analyze the components, the angular velocity vector represents the axis of rotation, as you can see in this picture. The unit axis of rotation would of course be this, the omega divided by the module. And then the speed of rotation will just be the module. And the angle of rotation with a speed given by this module for t seconds will be the product of these two. So while an alternative interpretation says that the rotation of an angle omega t about the unit axis omega divided by the module of omega is this expression. Let's see an example. Consider a vector of angular velocity, this one, and a value t equals 1. First we want to compute the matrix exponential, and then we want to verify that it is a rotation matrix. So let's compute the matrix exponential. We have this. We need the terms omega, the magnitude of omega, and then omega squared and omega hat squared. So we're going to compute that. These are, I call the needed terms, which are the ones that we will need. And then we replace these terms in this expression, and we just operate. By operating properly, we'll get that this is equal to this matrix. And then we can verify that actually the determinant is 1, so the determinant of this matrix is 1. And if you multiply this matrix with its transpose, it will be 1. It will be the identity. So it is a rotation matrix. Let's see now the Rodriguez formula in exponential form. We have seen this matrix before. Now we're going to see a simplification. If we use the unit angular velocity, and if we call the total angular displacement theta, which will be equal to t, then this expression can be simplified because this will be 1, this will be 1, this will be 1, and this will be 1. So we'll have just this. And this is called the Rodriguez formula, but you have to recall that the axis is unit. So the Rodriguez formula is a rotation matrix that represents a rotation of an angle theta about the unit axis omega. It's important to see that this is a unit axis omega. So we can represent any rotation about any axis of any angle by this exponential formula. Let's see an example. We want to determine the rotation matrix that represents a rotation of an angle theta about the axis 1, 0, 0 using the Rodriguez formula. The solution is this one. We have the Rodriguez formula and we have the terms that we need, and we just replace. If we want this axis, so x will be here, and then we will have this omega hat, and we just replace the terms, and at the end we get this. And you see that this is the rotation about x. So this is another way to derive the rotation about x. Now we want to determine the rotation matrix that represents a rotation of 30 degrees about 2, 1, 2. First, what we need to do is we need to have the unit vector. So we need the unit vector, which is this one. Now to get the unit vector, we divide this by its module. The module of this is the root square of 9, so it's 3. So we divide every term by 3. And then we get this omega hat, this skew-symmetric matrix, and we replace all these terms in the Rodriguez formula. And we just solve for that, and we get this matrix. We can verify that this is a rotation matrix by verifying its transpose, the product with its transpose, and the determinant. It must be plus 1. We have another Rodriguez formula, which is called the vector form of the Rodriguez formula. The objective here is to find the rotation of a vector, an angle theta, about the unit axis omega. The procedure is to apply the rotation matrix to rotate the vector, as we have seen before. But in this case, this rotation is generic, so we have to apply the Rodriguez formula to this rotation. So this rotation will be this exponential form of the Rodriguez formula. Now we just have to operate, we replace this, and we operate, and we apply properties of linear algebra, which you can see here. I won't go too much into the details, but if you want, you can follow this one step by one step. It's a step by step. And we have this expression. And this is the Rodriguez formula in vector form. But this Rodriguez formula applies directly the rotation to the vector. So this doesn't give a matrix. This applies directly the matrix to the vector. It can be sometimes computationally easier to apply this than to apply the previous one, but only if you are applying it to a vector. For example, we have this position vector, and we want to find the position after applying a rotation of 30 degrees about 2, 1, 2 using the vector form. And then we want to verify it using the rotation matrix. So using the vector form, first, this is the vector form, and we are replacing the angles. Then we replace just the elements, each of the elements here. So I'm just writing this in another form. This omega dot p is omega transpose p. I can replace this cross product using the skew-symmetric matrix. And I replace all the terms, and then I get that this is this expression, this vector. For the part B, I can first use the rotational matrix, which I computed in a previous example. So from the previous example, this was a rotational matrix. Now, if I multiply this rotational matrix with the vector P, I will get this. And this is equivalent to the previous vector that I just obtained, within some rounding errors. Just to end this part, let's see Lie algebra, which is more a mathematical concept. The Lie group associated with rotation SO3, if you remember SO3, capital SO3 represents all the rotational matrices. It has the associated Lie algebra SO3 in lowercase letters. The Lie algebra is the tangent space of SO3 at the identity element, and it represents the angular velocity. So all the angular velocity vectors lie in this Lie algebra space. It's given by skew-symmetric matrices, and this is a definition, that the matrix has to be skew-symmetric.